Good morning and welcome to this next lecture on sound and structural vibration. So last time we ended up with this Rayleigh integral, okay, and this time I said we will find an expression for sound radiation from a plate set in a rigid baffle. Okay, so my plate sitting in the xz plane. Okay, my plate sits in the xz plane. And let me say this, that this portion I am taking from the book by Frank Fahey, okay, and its title is somewhat Sound and Structural Vibration. Okay, and Radiation and Transmission or something like that. Okay, I'm taking directly from this book, so you can find these derivations there. Okay, so now this is my plate. This is my plate sitting in the xz exact plane, okay, and the response is in the y direction. Okay, so the plate extends between 0 less than equal to x less than equal to a and between 0 less than equal to z less than equal to b. Okay, and my velocity, panel velocity, is given by v tilde pq sine p pi x by a sine q pi z by b e to the power of j omega t. These are the mode shapes of a simply supported plate, okay, in the pqth mode, and this is the amplitude and this is the time indicator. It's harmonic forcing, sinusoidal. Okay, now in this derivation vpq will be held constant, even when omega changes, omega varies. Okay, normally if omega varies, the modal amplitude will change with frequency. If you go close to a resonance, it will go up. If you move away from a resonance, it will go down, etc. Okay, but we are not going to do that in this line of thought. vpq is going to be held constant. Okay, there's a reason for that, and it will become clear a little later. Now the pressure I want, x dash y dash z dash t, is equal to j omega rho 0 by twice pi. I am using rho 0 for my fluid density, v tilde pq e to the power of j omega t integral sine p pi x by a sine q pi z by b e to the power of minus j k r by r, okay, dx dz. Okay, this r carries the scalar distance of r dash minus r0, numerator and denominator. It is the distance between the source and receiver points. Okay. Now r of course has x and z dependence. R will carry x and z. Okay. So let's look at this. We have a panel okay. So the field point is at r bar, which is given by r theta phi in spherical coordinates. Okay, and theta is measured from vertical. Theta is measured from vertical, phi is measured this way. Phi is measured from here. Phi is measured from the x direction, and theta is measured from the vertical. Okay, the azimuthal angle, the elevation angle. Sorry, phi is the azimuthal, theta is the elevation angle. Okay, now we need the coordinates in rectangular description. Okay, so my y is equal to r cos theta, the y of this point, y value of this point is r cos theta, the x value is r sin theta cos phi, the z is equal to r sin theta sin phi. Okay, so this is the receiver, and the source point, its y is equal to 0, its x is equal to r, so we'll call it y0 x0, r0 is cos phi 0, and z0 is equal to r0 sin phi 0. Okay. So now we need to formulate this r, okay, which is the distance between r minus r0, okay, which we'll call r as r. So what is r equal to now? It is equal to the square root of x minus x0 whole squared plus y minus y0 whole squared plus z minus z0 whole squared. Okay. So in terms of the values we have found, this is equal to, okay, I'll just put a square root symbol to remember it is there. Okay, so what will we get? We'll get, okay, from here r square cos square theta, okay, from here plus r square sin square theta cos square phi, okay, and plus r0 square cos square phi 0. From here I'll get plus r square sin square theta sin square phi, from here plus r0 square sin square phi 0. Okay, and we have the coupling terms, the cross terms here, and there is a minus, okay, x minus x0 z minus z0 is a minus, so we will get minus twice r0 sin theta cos phi 0 minus twice r0 sin theta sin phi 0, all under the square root. Okay, so now this term here has this common cos square phi plus sin square phi. So this is r square sin square theta, then r square sin square theta plus r square cos square theta gives me r square. Now this gives me r0 square plus r0 square, okay, and I have minus twice r0 sin theta cos phi 0 plus sin phi 0. So cos of phi minus phi 0 and the root. This is r. Okay, so this is the one, this r will sit as e to the power of minus j k r and r in the Rayleigh integral. Okay, now, and this is going to be integrated over x and z. Okay, so the x and z will be part of the numerator here and part of the denominator here. Okay, and that integral is not amenable to closed form solution. Okay, if we write the integral which has sin p pi x by a sin q pi z by b e to the power of minus j k r by r, okay, where r contains xz, dx dz, this is not amenable to closed form solution. Okay, so in order to find a closed form, answer, we do what is called a far field approximation. That means my r is much greater than r0. r0 lies on the plate and r is the receiver, so r is much greater than r0. We do that. Okay, so if we do that, I'm sorry, this should be square. If we do that, we take r square outside, so it becomes r inside it becomes 1 plus r0 by r whole squared minus twice r by r0 sin theta cos of phi minus phi 0. Okay, and r over r0, I am sorry, r0 by r is much less than 1. So this carries one level of smallness and this carries the square level of smallness, so we will drop this term. Then what happens? We have r, capital R is equal to small r square root of 1 minus twice r0 by r sin theta cos of phi minus phi 0. Okay, and if r over r0, r0 over r is a small quantity like epsilon, then you can expand this and get r into 1 minus r0 by r sin theta cosine of phi minus phi 0, which is given by r minus r0 sin theta cos of phi minus phi 0. Okay. So now one more level of approximation. In the integral, this r goes in as e to the power of j k r or minus j k r by r. Okay, so that means what? It becomes e to the power minus j k into r minus r0 sin theta cos of phi minus phi 0 divided by r minus r0 sin theta cos phi minus phi 0. Okay. Now this is still not amenable, okay, still not amenable to closed form because we have xz here and xz over there. Okay. Now what we do is that it's like if I have an expression 1 minus epsilon, then I look at the expression cos of 1 minus epsilon, okay, is now suddenly in radians, versus I look at the expression 1 minus epsilon in just linear terms. Okay, so this is a nonlinear function of 1 minus epsilon, whereas here it's just a linear function. Okay. So if epsilon is a small quantity, it is safe to neglect epsilon over here. It is not so, it's not so safe to ignore epsilon over here where it appears as radians. Okay. So here in the numerator, even though r is bigger than r0, I have this expression, so I will not ignore this r0 term compared to this r term. Whereas in the denominator in comparison to r, this will be a small term I am going to ignore. Okay, so what will this look like? It looks like e to the power of j k r into e to the power of j I mean j minus j kr e to the power j k r 0 sine theta cos of phi minus phi 0. In the denominator we will take it as r. Okay, that is the approximation. So now if we put all this together, my solution here, pressure at a certain location r, okay, including time, let us say, including time. I often forget to put the time part because these are harmonic, so they do not hurt us very much. So j omega rho 0 v tilde pq divided by twice pi e to the power of j omega t, that is your time, then e to the power of minus j k r fell out of the approximation, and now the integral. Okay, I am going to write the integral, I am going to write it here. Integral goes from 0 to a, integral goes from 0 to b sine p pi x by a sine q pi z by b, and here we have e to the power. Now if you remember, r0 sine theta cos phi we will have here is r sine theta cos phi is x, okay, and r sine theta sine phi is z, okay. So however now it is r0, it is r0, so this is going to be e to the power j k r0 sine theta into cos phi 0 plus sine phi 0 dx dz. However, r0 cos phi 0 is x and r0 sine phi 0 is z, okay. So this becomes p some location r and t, this entire term in front here, double integral 0 to a, 0 to b, then sine this term, sine this term, and e to the power of jk x sine theta cos phi plus z sine theta sine phi dx dz. Okay. Now this has to be integrated, okay. This has x only, this has x only, you have dx. This has z only, there is z only, here you have dz, okay. So you can use the product rule and integrate them separately, okay. So what is the final result? The final result, okay, now I write as pressure at a certain scalar r theta phi time is given by j v tilde pq k rho 0 c e to the power of minus j k r over twice pi r a b over p q pi squared into a term now, this term which I am going to write here. What is that? It is minus 1 to the power p e to the power of j alpha minus 1 by alpha by p pi whole squared minus 1, this is one term, multiplied by minus 1 to the power q e to the power j beta minus 1 divided by beta by q pi whole squared minus 1. So, this total term enters this box here, okay, where alpha is equal to k a sin theta cos phi, whereas beta is equal to k b sin theta sin phi. Now, we are interested in the far field sound intensity. Sound intensity, okay, in the far field. So, those who remember their acoustics, it is given by I as half real part of P V conjugate, which is also equal to 1/2 magnitude of P tilde square by rho 0 c. Okay, I do not remember what I have been using for c, rho 0, been using c, okay, rho 0 c. Okay. So, this is the plane wave. By this time the wave has become a plane wave. Okay. So, now pressure was found earlier. If we use this expression now, my intensity in the far field is going to be twice rho 0 c v tilde pq squared, okay, into k a b by pi cube r p q squared, okay, into cos or sine of alpha by 2, okay, into cos or sine beta by 2 divided by alpha by p pi whole squared minus 1 into beta by q pi whole squared minus 1. This whole thing is squared. Okay. Now, here what is this new notation here? Cos will be used when P or Q, P comes in here, okay, and Q comes in here. The cos will be used when P or Q are odd, okay, and the sine will be used when P or Q is even. Okay. We are running out of time, so I will stop here. We will continue in the next class. Thank you.